Hello everyone, welcome back to my channel. In the last video, we discussed the concept that is phases and its applications. So what happens when the alternating voltage applied to a inductor, a capacitor and a resistor, and what is the phasor diagram for that each element. So let us discuss in this class, that is impedance. So impedance in the sense the effective opposition offered by the capacitor, inductor or resistor or combination of capacitor inductor or capacitor resistor, inductor and resistor to the flow of alternating current, that we can call it as an impedance. In the sense the effective opposition offered by these capacitor, inductor and resistor to the flow of alternating current, that we can call it as impedance. So that can be represented by Z. Now we know that expression, that is the peak value of a current that can be represented by I naught, which is equal to V naught divided by Z. Here Z is nothing but impedance. We know that if Z is equal to R for a purely resistive circuit, if Z is equal to chi of L, here chi of L in the sense inductive reactance. Here Z is equal to chi of L, which is for purely inductive circuit. Similarly, Z is equal to chi of C, the chi of C in the sense a capacitive reactance, and Z is equal to chi of C is for only a pure capacitive circuit, and the Z is nothing but a impedance. Here they explain about one concept, that is a phase factor. Here a phase factor in the sense phase factor that can be represented by pi. Here we know that sinusoidal variation of a voltage and a sinusoidal variation of a current that can be represented by an expression V is equal to V naught sine of omega t. V is equal to V naught sine of omega t, and I can be written as I is equal to I naught sine of omega t plus pi. Here this pi represents a phase factor. If pi which is equal to 0, in the sense the phase difference between that voltage and the current which is equal to 0. If pi which is equal to 0, this is for only a resistive circuit, because in the last video we discussed that when an alternating voltage is applied across a resistor, there the phase difference which is equal to 0. Therefore here we took a pi which is equal to 0. If we consider pi which is equal to minus of pi by 2, the value that is minus of pi by 2, and this is for only inductive circuit. We discussed in the last video, when an alternating voltage is applied across an inductor, there the phase difference which is equal to minus of pi by 2, because the current lags behind the voltage by pi by 2 there. Here for inductive circuit. Similarly, pi which is equal to plus pi by 2 in the sense we discussed by considering a capacitor. What happens when the alternating voltage is applied across a capacitor? There the phase difference is pi by 2, because current leads the voltage by pi by 2 there, and it is for purely capacitive circuit. So this is about the introduction part of this concept, that is impedance and a phase factor. Next, the combination of inductance and resistance in series. Combination of inductance and resistance in series. So let us consider this one as an inductance of an inductor that can be represented by L, and the resistance of a resistor that can be represented by R. So when these two are connected in series, the voltage across an inductor that can be represented by VL, and the voltage across a resistor that can be represented by VR. Now we know that the sinusoidal variation of voltage or the alternating voltage across an AC source that can be represented by V is equal to V naught sin omega t. We know here V in the sense instantaneous voltage, V naught that represents a peak value of voltage, and omega that represents angular frequency. And in case of current, I is equal to I naught sine of omega t plus or minus pi we are going to get. Here plus or minus pi that represents a phase difference. Here in this case inductor and resistor they are connected in series, therefore the current flows through these electrical elements remains same, but the voltage across an inductor and voltage across resistors are different, and we have to take a sum of those. Now the peak value of voltage across inductor and resistor that can be represented by your peak value of resistor that can be represented by I naught into R, and the peak value of inductor voltage across an inductor that can be written as I naught into chi of L. Here I naught that represents a peak value of a current, chi L that represents inductive reactance. If we observe the vector diagram for this one, in vector diagram, so we are going to observe a vector diagram like this. So by observing this vector diagram, here OA that represents voltage across a resistor along x axis we are considered, and OB that represents VL voltage across an inductor, so along y axis we took, and here OC that represents a resultant vector of these two, voltage across a resistor and voltage across a inductor, that can be represented by a peak value of voltage, that is V naught. By applying a Pythagoras theorem, so here V naught square for this triangle OAC, V naught square which is equal to VR square plus of VL square. We know that VR in the sense I naught square into R square plus of VL in the sense I naught square chi of L square we are going to get. Now this can be written as I naught square into R square plus of chi of L square. We took I naught as a common term, so this represents V naught square. Now V naught which is equal to I naught under square root of R square plus of chi of L square we are going to get. If we simplify further, here I naught which is equal to V naught divided by square root of R square plus of chi of L square we are going to get. Now we know that I naught which is equal to V naught divided by Z. If we compare these two expressions, so we are going to get Z is equal to under square root of R square plus of chi of L square. Here Z is equal to under square root of R square plus of chi of L in the sense omega square L square we are going to get. This is an expression for the impedance in case of combination of inductance and resistance in series. We know that the voltage across a resistor which is a phase with current, we discussed this, the voltage across a resistor with phase with a current, but the voltage across an inductor is not in phase with current. There is an angle formation between the current and voltage, that angle is 90 degree, that is pi by 2. Therefore, VR is in phase with current, VR is in phase with current, but VL is not in phase with current. Therefore, so we are going to get the phase angle. Based on that, the current in the combination of inductance and resistance in series circuit is I is equal to I naught sine of omega t minus of pi. Therefore, I is equal to I naught sine of omega t, this one is plus, value of pi is minus pi by 2, and this is the current flows through that L R in series circuit. And we know that the phase angle between the current and voltage, the phase angle, so that can be represented by a tan of pi, which is equal to your pi, which is equal to opposite divided by adjacent. Your opposite we took VL, and adjacent we are going to get a VR. So, VL in the sense we are going to get I naught chi of L divided by, so VR in the sense I naught into R. Therefore, so here I naught gets cancelled, omega L is nothing but chi of L is nothing but omega L divided by R, and this represents a tan of pi. So, this we are going to give the phase angle between voltage and current. The next concept is combination of capacitance and resistance in series. Combination of capacitance and resistance in series. So, for that, let us consider this one is on capacitance of a capacitor and a resistor. Those two are connected in series. The capacitance of the capacitor that can be represented by C, resistance of a resistor that can be represented by R, and the voltage across a capacitor, that is Vc, and voltage across a resistor that can be represented by a VR. Now, the alternating voltage across an AC source that can be represented by V is equal to V naught sine of omega t. We know that V naught is the peak value, omega is an angular frequency, V represents instantaneous voltage. Now, the capacitor and resistor, they are connected in series. Therefore, the same current flows through that circuit. The same current flows through that capacitor and inductor. And we know that the current through that a circuit that can be written as I is equal to I naught sine of omega t plus or minus pi. Here, the capacitor and resistor we are using. Resistor is in phase with the current, but the capacitor is not in phase with the current. Therefore, so either it may be a lags or ahead takes place in that current. Now, the peak value of voltage across capacitor and a resistor. Let us consider a Vc, which is equal to the voltage across a capacitor that can be written as I naught into chi of C. Your chi of C that represents capacitive reactance. That capacitive reactance, it is also called as 1 over omega C. Now, the voltage across a resistor that can be written as I naught into R. Here the combination of a capacitor and a resistor. Resistor is in phase with current, but the capacitor is not in phase with current. Based on that, if we observe a vector diagram, in vector diagram, so let us consider along x axis I naught, this one is A, V or V took, along y axis, that is B VC, the resultant of VR and VC, that gives a peak value of a voltage, and this is an angle pi. So, in vector diagram we are going to observe OA which is equal to VR, the voltage across a resistor along x axis, OB which is equal to VC, the voltage across a capacitor along a negative y axis, and OC which is equal to V naught, the resultant of these two vectors, that gives a V naught. So, in this case the current leads the voltage by pi by 2, the current leads the voltage by pi by 2. By considering the triangle OAC, so V naught square which is equal to VR square plus of VC square. We know that VR square in the sense I naught square into R square plus of VC square in the sense I naught square into chi of C square, and take a I naught square as a common term, R square plus of chi of C whole square, we are going to get R square plus of chi of C square. Now V naught which is equal to I naught under square root of R square plus of chi of C square. Therefore, I naught which is equal to V naught divided by square root of R square plus of chi of C square, we are going to get. And if we compare this expression with I naught is equal to V naught divided by Z, we are going to get Z is equal to under square root of R square plus of chi of C square. So, this can also written as R square plus of 1 divided by omega square L square, we are going to get, and this is the value of impedance in the combination of capacitance and resistance in series. So, we know that in the combination of a capacitor and resistor, in case of a resistor is in phase with a current, but the capacitor is not in phase with current. We know that I is equal to I naught sine of omega t. Your resistive circuit and capacitive circuit, what we are going to say, and these voltage across a resistor and voltage across a capacitor are mutually perpendicular to each other. Therefore, the angle between these two is pi by 2. Here I naught sine of omega t plus of pi, and here I naught sine of omega t plus of pi by 2 we are going to get, and this is an expression for a current. And if we go for the phase angle in the sense the angle that is pi, tan of pi is equal to VC divided by VR. Here voltage across a capacitor and voltage across a resistor. Here voltage across a capacitor that can be represented by I naught chi of C divided by voltage across a resistor is I naught into R. I naught gets cancelled. Therefore, tan of pi which is equal to chi C in the sense capacitive reactance that can be written as 1 over omega C. Therefore, 1 divided by omega C into R we are going to get, and this is an expression for a tan of pi which is equal to 1 over omega C into R for phase angle, and this is about the combination of capacitance and resistance in series. And the next concept is combination of capacitance and inductance in series. Now we know that let us consider this one as a capacitor which is connected with a inductor in series across AC source. The capacitance of the capacitor that can be represented by C, inductance of an inductor that can be represented by L. Now voltage across a capacitor Vc, voltage across an inductor, that is VL. We know that the voltage across an AC source that can be represented by V is equal to V0 sin omega t, and the peak value of a current across a capacitor and a resistor that can be represented by the peak value of voltage across capacitor and inductor. So that can be represented by Vc, which is equal to I0 chi of L, that is capacitive reactance. This can also written as I0 divided by omega c. So VL, which is equal to I0 chi of L. So this can be written as I0 omega L. Here we have to know that capacitor and an inductor, these two are which is having a phase difference with a current. The voltage across a capacitor, which is having some phase value with a current, that is a pi by 2. Similarly, voltage across an inductor which is also in phase with current by pi by 2. Therefore, the voltage across a capacitor and voltage across an inductor both are in opposite in direction. Therefore, the phase difference between voltage and capacitor, the phase difference between voltage across a capacitor and voltage across an inductor, that is the phase difference between voltage across a capacitor and voltage across an inductor is pi, and which is opposite in direction, opposite in phase we are going to get. So if you observe the phasor diagram or a vector diagram, in vector diagram we are going to observe vector diagram like this. Let us consider this one as a VL, VC, the difference of this one is VL minus of VC. Here it is angle is pi by 2 and angle is pi by 2. Now OA that represents voltage across an inductor, OB that represents voltage across a capacitor, OC that represents a resultant voltage, that is V0, is equal to that VL minus of VC. The phase difference between voltage across a capacitor and voltage across a inductor is 90 degree, that is VL minus of VC. Now the potential difference, that is V0, which is equal to the difference of voltage across a inductor and voltage across a capacitor. Therefore, we are considered V0, which is equal to VL minus of VC. Now V0, which is equal to VL, is nothing but I0 L minus I0 chi of C. Now V0, which is equal to I0 is a common term, chi of L minus of chi of C we are going to get. So I0, which is equal to V0 divided by chi L minus of chi C we are going to get. So if we compare with an expression I0, which is equal to V0 divided by Z, here Z, which is equal to chi of L minus of chi of C. This can also written as omega L minus of 1 divided by omega C, and this is an expression for the impedance in the combination of capacitance and inductance which are in series. Now, what happens if capacitive reactance and inductive reactance both are equal? If the capacitive reactance and the inductive reactance both are equal, so then the circuit which is called as a resonance circuit, or that circuit we can also call it as electrical resonance. Here chi of L is equal to chi of C, we are going to get chi of L that can be written as omega L, which is equal to chi of C that can be written as 1 over omega C. If we cross multiply this one, omega square which is equal to 1 divided by L into C, we are going to get. Therefore, omega which is equal to 1 divided by square root of L into C, we are going to get. Therefore, omega that can be written as 2 pi into nu, which is equal to 1 divided by square root of LC. Here nu which is equal to 1 divided by 2 pi square root of L into C, we are going to get. And this is an expression for a resonant frequency. Here the resonant frequency in the sense, the frequency in which the current flows through that circuit is a maximum, that we can call it as a resonant frequency. So in the sense the current flows through this circuit is maximum, and this is about the combination of capacitance and inductance in series. And the next concept is combination of inductance, capacitance and resistance in series. Let us consider the circuit diagram, the combination of inductance, capacitance and resistance. They are connected in series across an AC source. Let us consider inductance of an inductor L, capacitance of the capacitor is C, and the resistance of that resistor is R. Now, when the current flows through that circuit, the voltage across an inductor is VL, voltage across a capacitor is VC, and the voltage across a resistor that can be represented by VR. We know that the alternating voltage across an AC source that can be represented by V is equal to V naught a sine of omega t. And we know that inductor, capacitor and resistor, they are connected in series. Therefore, the same current flows through that each element because they are connected in series. Now, the peak value of voltage across inductor, capacitor and resistor, that can be written as voltage across an inductor is I naught chi of L. This can also written as I naught chi of L in the sense omega L. Here chi L that represents inductive reactance and I naught represents peak value. Vc, which is equal to voltage across a capacitor I naught into chi of C. This can be written as I naught divided by omega C. Here chi of C in the sense the capacitive reactance, that can be written as 1 divided by omega C, and VR, which is equal to the voltage across a resistor, that can be written as I naught into R, we are going to get. And the voltage across the inductor also, which is having a phase difference value, its value is pi by 2. But in case of voltage across a capacitor with a current, here voltage across a capacitor is lags behind the current by pi by 2 value. Here voltage across an inductor is leads the current by pi by 2. So based on this, they explain vector diagram. In vector diagram, so this one represents the I naught VR along x axis and VL along y axis and VC along negative y axis, and here it is D, its value is VL minus of VC. And this represents OE. Now OA, that represents a voltage across a resistor along x axis. OB, VL voltage across an inductor. OC, voltage across a capacitor. OD, a resultant voltage of voltage across a capacitor, voltage across a inductor, or voltage across a resistor, that can be represented by VL minus of VC. Here this one we are going to get if VL is greater than VC. If VC is greater than VL, that time we have to consider VC minus of VL. Now OE, that represents a resultant vector of this voltage across a resistor, voltage across a capacitor, voltage across inductor, that can be represented by V naught. So from this vector diagram, we are going to observe, according to Pythagoras theorem, for this triangle OAE, so V naught square, which is equal to VR square plus of VL minus of VC whole square. Now V naught square, which is equal to I naught square into R square plus of, so here VL in the sense I naught chi of L minus of I naught chi of C whole square we are going to get. V naught square, which is equal to I naught square R square plus of I naught square into chi of L minus of chi of C whole square. V naught square, which is equal to I naught square into R square plus of chi of L minus of chi of C whole square. So here V naught, which is equal to I naught square root of R square plus of chi of L minus of chi of C whole square we are going to get. Therefore I naught can be written as V naught divided by under square root of R square plus of chi of L minus of chi of C whole square. If we compare with an expression, I naught, which is equal to V naught divided by Z, here Z is equal to, compare this and this expression, R square under square root of R square plus of chi of L minus of chi of C whole square. Now we know the value of inductive reactance and capacitive reactance, so that can be written as R square plus of omega L minus of 1 divided by omega C whole square, and this is the final expression for the impedance for combination of inductance and capacitance and resistance in series. And if you like my content, please subscribe my channel and click on the bell icon. Thank you.